Okay, so earlier we had seen the different types of representations. One is your transfer function representation of the system, another is the state space representation. Hmm. We had also, so these are the mathematical definitions uh, or representations of a dynamical system. Uh, Pictorially, we also did the analysis based on the block diagrams and also the state diagrams. Okay. Now in the transfer functions, we had done our analysis to compute the solution of a system in the time domain. Say for example, if you have a transfer function ys over rs, some transfer function t of s, then from here we have computed y of t in the time domain for some specific signal r of t which was given to us. Now this r of t could be step signal or a ramp signal or a parabolic input. Now as an equal as an equivalent representation we have introduced the state space. And the idea behind introducing the state space representation is to represent a higher order differential equation into a first order differential equation. Okay, meaning to say that given this, say for example, we have a third order system which is d cubed by y by dt cube plus 5 d square y by dt square u of t. Okay, let's say we have this differential equation given to us. So you know how to compute the transfer function, that is y over u. So the idea here is, you see that we need to compute the three derivatives of the signal y. Now in being in the or staying in the time domain itself, we could represent this differential equation into a first order differential equation by introducing the variable x, which is the state variable, as dx by dt as ax plus bu. Okay, where a we have computed, or you can compute by yourself using the methods introduced earlier, as it is one of the canonical forms, and b is 0, 0, 1. Okay, so while doing this uh, or representation from higher order differential equation to first order differential equation, we get to understand that now a b could be matrices. Okay, now when we have the matrices as a first order differential equation, how to first of all we will see that how to compute the solution and what are the properties associated with the solution of the system or this representation that we could relate with the analysis we had done earlier based on the transfer function. Okay, so the first concept we introduce about the state transition matrix, which would help us to write the final solution of the state space system. Okay, so starting with this differential equation, let's consider only the homogeneous part only, meaning to say that u is equal to 0, and first of all we'll see the solution of the homogeneous system, and then we will see how it could be how it can be generalized for the system or the forced systems. So let's write the homogeneous linear state equation as dx by dt is equal to ax, where x is a vector, a is a matrix, and here we define the state transition matrix as some phi of t, which is of n cross n dimension. It is also a matrix, and it satisfies this differential equation, meaning to say that satisfying this differential equation, meaning to say that if I replace x by this phi of t, then this equation should also satisfy. That is to say, d phi by dt is equal to a phi of t. Okay, now the relationship between the state vector and the state transition matrix is, say suppose we are given some initial condition x of 0 at t is equal to 0, then your x of t is basically phi of t times x of 0. Okay, now if you substitute this equation here, you would obtain this one, and you can verify by yourself. So this is the solution of this. This is the solution of this the linear homogeneous state equation. Now the next question arises here: how to compute the state transition matrix phi of t? So one method, what you have been doing from the beginning, is by using the Laplace transforms onto this equation, you can compute the state transition matrix. Okay, so if I take the Laplace transform of this equation, I would obtain, by using the property of the Laplace transform, is x of s minus some initial condition x0 is equal to a x of s. Okay, so I can represent x of s as psi minus a inverse x of 0. Okay, here we have assumed that this matrix Si minus A, where I is an identity matrix and where S is a complex variable, I is a identity matrix of the same dimension of the matrix A, and we have assumed that Si minus A, which would again be a matrix, is non-singular, because if it is non-singular, then its inverse won't exist. Okay, now for computing the time domain solution, we take the inverse Laplace transform both sides of this equation, and we would obtain x of t as Laplace inverse of Si minus A inverse x naught for all t greater than equal to 0. Okay, now if you see the similarity between this equation and this equation, you would notice that phi of t you can compute by taking the Laplace inverse of Si minus A inverse. Okay, so this is our state transition matrix. So let's denote this STM, state transition matrix. Okay, and another way of computing this state transition matrix is, now without taking the or without utilizing the Laplace transform, is, so we'll see, begin with this equation once again, which is dx by dt is equal to ax. Okay, so now this is a first order differential equation, and you know at the outset that the solution of a first order differential equation is basically given by x of t is equal to e to the power at x naught. Okay, or assume that this is a solution of this homogeneous system, and this exponential, where we know that A is a matrix, can be represented as, by using the Taylor series, is I plus, or if I expand this e to the power at as I plus at plus 1 over 2 factorial a square t square, and I will go on. So just to verify whether this x of t is basically the solution of the homogeneous state equation. So let's, to validate this, we'll take the derivative of this exponential term. So d e to the power at dt. So here you would notice that the derivative of this exponential term is basically given by a e to the power at. You can verify from this expansion of the exponential term. So you see here that this again brought us back to this equation. If you see again the similarity between this equation and this equation, your state transition matrix basically is given by phi t is equal to e to the power at. Okay, now whatever the properties of the matrix exponential terms are there, uh, those will become the properties of the state transition matrix. So one of the properties is if that if I put t is equal to 0, if I compute the state transition matrix at t is equal to 0, that is phi of 0, I would obtain the identity matrix, and this you can verify by putting t is equal to 0 into this equation. Okay. The second property is that if I take the inverse of the state transition matrix or the phi, it we would have phi of minus t. Okay, for the proof you can, I think you can do by yourself by analyzing this exponential series. So this is the solution of the homogeneous state equation. Now let's generalize the solution for the complete state space system by considering the force system, meaning to say where u is not equal to 0. So we have dx by dt is equal to ax plus bu. Okay, again analyzing the solution of this system by taking the Laplace transform. So I can take the Laplace transform both sides of this equation to finally write sxs minus x of 0, and the right hand side I would have bu of s. So computing x of s from this equation, I would have x of s is equal to si minus a inverse x naught plus si minus a inverse bu of s. Okay, now x of t, by taking the Laplace inverse Laplace transform of this equation, I would have Laplace inverse of si minus a inverse x naught, which is basically the solution of the homogeneous equation, plus Laplace inverse of si minus a inverse bu. Okay, now here I can use the property of the Laplace transform, that here we are doing the multiplication in the Laplace domain, which would become the convolution in the time domain. So the solution of this first term is basically phi of t x naught. This we have seen already because this term is the state transition matrix, plus using that property the Laplace inverse would become the convolution, meaning to say 0 to t phi t minus tau. Phi basically comes from the Laplace inverse of this thing times b u tau d tau. Okay, this is the complete solution in the state of the state space. So if you recall, we also have the output equation, but the output equation is basically the algebraic equation with no integral derivative terms. So cx plus du. So whatever the x we have obtained here, I will directly substitute here to finally obtain y. Okay, this is how you can obtain the solution of the state space systems. Now we shall see the other irrelevant information from the state space system, that is the characteristic equations, eigenvalues, and the eigenvectors. So suppose given a differential equation of nth order dn by dt y plus an minus 1 as we go on a naught y of t. This equation we have been seeing from the signal and system course, b naught u of t. Okay, where we it is presumed that n is greater than m. Okay, and by defining the operator d by dt and its derivatives as some xi of k for k is equal to 1 to n, I could write the differential equation as xi n plus a minus 1 xi n minus 1 plus a1 xi plus a naught is equal to, similarly on the right hand side, bm b naught u. Now the characteristic equation of this system is obtained by setting the homogeneous part of this equation to 0. Okay, so the characteristic equation basically is given by not equal to 0. This becomes our characteristic equation. Okay, and similarly if you see from the transfer function, if you put the denominator polynomial of the transfer function is equal to 0, then it becomes your characteristic equation. Now seeing from the transfer function, so we had seen earlier the relationship between the transfer function and the state space representation, meaning to say if I want to obtain a transfer function from the given state space representation, then that relationship is given by this is y over u g of s is equal to c adjoint of si minus a divided by si minus a b plus t. Okay, and let's call it, put it in the mod, meaning to say we are computing the determinant of this matrix. So this becomes the denominator polynomial. Now if I put it equal to 0, which is mod si minus a equal to 0, then it becomes the characteristic equation. Okay, and by putting this mod I simply means to compute the determinant. You can also express this as determinant of si minus a equal to 0. Okay, now the roots of the transfer function we have defined as the poles, and here if I compute the roots of this equation, characteristic equation, we call them the eigenvalues. Okay, the roots of this characteristic equation becomes the eigenvalues, and the any non-zero vector, let's call it pi, that satisfies the matrix equation for some lambda I, let's say lambda I minus a, where a is the state matrix of the state space representation, and that vector pi is equal to 0. Okay, and these lambda i's are the ith eigenvalue of the matrix A, and the eigenvalue of matrix A you can compute from here. Okay, so these are the some associated concepts with the state space systems. How to compute the characteristic equation, its solution, how to compute the eigenvalues and the eigenvectors from a given state space representation. The other canonical forms we had seen earlier already, that there is no unique representation of the state space, and we had studied some specific controllable canonical form and the observer canonical form. So both those representations we will see at the later part of the course, when we will come on to the controller designing aspects in the state space. Okay, so I think I can stop here because this finishes our some basic analysis of the state space systems. If you have any queries or doubts, I can take them now.